We know already that any moving charge creates a magnetic field. We also know that a moving charge or a current in a magnetic field experiences a force. And this is where it gets fun. We're going to bring those two ideas together with a flourish and look at the force between two current-carrying wires. We're producing a magnetic field and we're looking at the effect of that magnetic field on the current-carrying wire. Over here we have a wire, and it is going, well, I'll let you think about it. Is it going into the page or out of the page? It has a little cross, so that's the back of the arrow, so it's heading away from us. We can use our right-hand grip rule to figure out what direction the magnetic field is going around that wire. So we use our thumb in the direction of the current, which is going away from us, and our fingers coil around, and they're going around and around that wire in the clockwise direction. So I'll just draw a couple of those loops around here like this. So it's going in the clockwise direction. And if you can't figure that out, you need to go and look at your right-hand grip rule again. So we go further and further away from this wire, further over in all directions, and it will still be going clockwise around that wire. Let's have another look at a wire in the vicinity of that first wire, also with its current going into the page. And we're going to have a look at what effect will be happening on that wire. So if we consider the magnetic field due to that first wire is always going down the page. So I've just been drawing that magnetic field going down the page as we get further and further away. Now this is really schematic. Of course, that magnetic field will be getting less strong, and so those magnetic field lines really probably should be drawn further apart, but for now we'll just leave them as they are. So at the position of this blue wire here, the magnetic field is going down the page. So now we need to use our right-hand slap rule to figure out what direction the force will be on that wire. So right-hand slap rule, many fingers, many magnetic field lines going down the page. The moving charges, and this is the way I like to think of it, the moving charges in that wire are not going into the page, because that's the direction of the current. The electrons are actually coming out of the page. So our thumb will be coming out of the page. And the force on that wire, because we're talking about negative charges moving, if you're in the same kind of convoluted shape with your arm as I am at the moment, which is rather uncomfortable, thumb coming out of the page, fingers going down the page, the back of your hand, which will be the force on the negative charges in that wire, which are moving, would be to the left. And so the force on that wire will be to the left. And here's that force there. Of course, you can do exactly the same thing by looking at the magnetic field due to this wire here and find that they're also going clockwise, but they're going up on that side. All right, you can have a look at what the magnetic field will be like over here, and it will be going up the page. Do exactly the same situation and discover the direction of the force, and I'll let you do this one. The direction of the force on that orange wire will be going to the right. So here it is, getting a bit complicated in here, sorry, there's the force going to the right. This is a bit of a messy diagram, but it shows you how each wire is setting up a magnetic field around itself, and that interaction of the moving charges with that magnetic field, well, that's the way we can think of it, which causes a force. So when we've got two wires going the same direction, they experience a force of attraction. They are pulled together, and for two wires you can show going in opposite direction, the current going in opposite direction, they will be repelled from each other. Now this diagram is not really instructive to describe what the magnetic field is like between those two wires. I'm going to just take this and just shift it up here a bit, and I'm going to copy in the real shape. If you added those two magnetic fields together, what it would look like. So here's one I prepared earlier. Two wires. You can look at how those two magnetic fields, which are vectors, remember, how they add up in all these different places. And in the middle, between the two wires, they kind of cancel out a little bit. And so you're left with kind of a space with less magnetic field strength there. And you can kind of almost think of it, well, there's a big gap there. Those two things want to be pulled together to fill that gap. That's just one way of visualizing what's happening. And here's another one that I prepared earlier, and you can do that same trick. I'll leave you to do that, and we can look at it in class to show that the magnetic field between two wires which are carrying currents in the opposite direction are repelled. So to determine the direction of a force, step 1, use the right-hand grip rule to determine the magnetic field direction due to wire 1 at the position of wire 2. Step 2 is to use the right-hand slap rule to determine the force on the current carrying wire number 2 due to the magnetic field created by number 1. So of course we can use some equations to quantify this. We need to combine the equation that describes the magnetic field around the current carrying wire with the with the force experienced by a wire due to some magnetic field. And here they are. If we substitute one of these into the other, and we can go through this in more detail in class, we can find the force on wire 1 as a function of the current in both of the wires and the common length of those wires and the distance they are apart. So here's our equation. The force on wire 1, F1, is got increases as either of the currents increases. It increases if the length, the common length, so the length that are exposed to each other, if you like, that are next to each other, if that increases. And as they get further apart, so as R goes up, the force will go down. They're inversely proportional. And that's it. Of course, this also applies to the force on wire 2. So all these things could be interchanged. And of course, the force on wire 1 will be the same as wire 2 because they will have exactly the same numbers over here.
It's interesting to note at this point that the unit of current, the ampere, is actually defined in terms of this equation. If we have two wires each that are 1 meter apart from each other, and they each experience a force of 2 by 10 to the minus 7 newtons, so either attraction or repulsion depending on the directions of those wires, then the current through those wires is defined as 1 amp. So that is the actual definition of the amp. Next, we're going to talk about induction, and that's really cool. I'll see you in the next video.